Okay, just a quick recap before we begin. In the last class, I introduced two new inequalities. One, the data processing inequality, which says that if x, y, z form a Markov chain, then the mutual information between x and y is always greater than or equal to the mutual information between x and z. Another way of saying this is if you have some y that is dependent on x, then any further processing of y to give you any random variable z is not going to give you any more information about x than y can. All right. And we also looked at Fanos inequality, which is a very useful tool to prove lower bounds. And this says that, again, if you have x and which you want to estimate or infer about, but you get to observe y, and then you sort of decode from y to get an x hat, which is an estimate of x, then Fanos inequality connects the residual information or the residual amount of randomness left in x given y to the probability of error of x hat. So the conditional entropy of x given y, which again just by using data processing inequality is less than or equal to the conditional entropy of x given x hat, is upper bounded by this function of the probability of error. So if the probability of error is small, then it should naturally mean that there is not much uncertainty left in x anymore given x hat, or there's not much randomness left over in x given y. Right? And we use this to prove a lower bound on the compression rate or asymptotic compression rate of any fixed length compression scheme. Using Fanos inequality, we saw that irrespective of how you construct your encoder and decoder, as long as they are deterministic, any fixed length compression scheme has to have a rate which is at least the entropy rate minus some quantity that is determined by the probability of error. So if you want the probability of error to be vanishing in n, then the asymptotic compression rate is at least the entropy rate. All right. So in previous classes, I defined the entropy, or we've seen entropy in the context of compression. Right? We formally studied the problem of variable length compression and now very briefly fixed length compression, and saw that the entropy arises as a natural fundamental limit to the rate of compression that can be achieved. But I keep talking about entropy as a measure of randomness in the system, or the measure of randomness of the random variable x. So is there a way of formalizing that, or what is the intuition behind that? So in the original paper, Shannon introduced entropy as a measure of randomness or uncertainty in a random variable through an axiomatic framework. So suppose we had a measure of randomness of a particular distribution, then what properties should it naturally satisfy? And if it has to satisfy those properties, then what are the possibilities? What kind of functions satisfy those particular properties? Right. So that's an axiomatic approach, and depending on how you choose, you can make minor changes to the axioms and potentially get a different measure of uncertainty. But entropy can be derived using the following axioms. All right. So let's say that I define some function hm. So on nm symbols, suppose I have some probability mass function on nm symbols. Let's call the probabilities p1, p2, p3 up to pm, and let hm be any function which is guaranteed to be non-negative and satisfies the following properties. So the first property is that it should be permutation invariant. In other words, if you change the order of the probabilities, the order of the PIs, then the value of Hm should be the same. So in other words, Hm of P1 through Pm, this is equal to Hm of P pi of 1 up to P pi of m for any permutation pi. We've already seen that entropy satisfies this property. The second property is what is called expansibility or expansion. So let's say that one of the probabilities is equal to 0. One of the probability values is equal to 0. Then this should be equal to Hm minus 1 on the reduced alphabet. P1 up to Pm minus 1. So adding in more symbols with 0 probability should not really change the amount of randomness in the system. Right? Again, both of these requirements are very natural because just changing the labeling does not change the amount of randomness in X. And similarly, adding more dummy symbols with 0 probability cannot really increase the randomness in X. The third is just a normalizing constant, because you need to say, in principle, if you have one measure of randomness, then any scaled version of that can also be a good enough measure of randomness. Right? So in order to do that, we normalize as to what it means to be one bit of randomness. And that can be seen because suppose I have a fair coin flip. Right? So I have two outcomes. With probability half I get a 1 and a probability half I get a 0. Then it's natural to say that this gives one bit of information because of our natural intuition as to what it means to be one bit. So we'll say that if I have a PMF, which is half-half, then it should contain one bit of information. So this is the unit. Next I have subadditivity. So loosely speaking, if I take two random variables, put them together, then or take them as a collection, take a pair of random variables, then the total amount of uncertainty, when I have both x and y together, cannot exceed the uncertainty that is there with x alone plus the amount of uncertainty that is there in y alone. Right? Because just by combining the two, you shouldn't get any more randomness. So h of x comma y should be less than or equal to h of x plus h of y. So to put that more formally, suppose I have h mn for two positive integers m and n, Suppose I have an R1, R2 up to Rmn, or let me label them as R1, R11 up to R1n, R21 up to R2n, and so on all the way up to Rmn. So this is a joint PMF corresponding to a pair of random variables x and y. X has cardinality m and y has cardinality n. Then this quantity should be less than or equal to hm of p1 up to pm plus hn of q1 up to qn, where p and q are the corresponding marginals. So pi is basically summation I equal to 1 to n of r ij, and qj is, let me use something different, this should be j, and qj is summation I equal to 1 to m r ij. So I can write all of the probabilities Rij's in the form of a table. So this is some joint distribution. So Pi corresponds to the marginal of each row, of the ith row, and Q corresponds to the marginal corresponding to each column. Question?
So, in the case of thermodynamics, so if you mix two gases, then the total entropy of the mixture increases from the entropy of individual gases. So, but here it is not the case.
This is not the case. So we're just defining some measure of randomness here. What we would expect a measure of randomness in a pair of variables. Right? Again, you shouldn't draw one-to-one parallels with a thermodynamic system. All right? The entropy that you see in a thermodynamic system is different from the entropy of a random variable. There are some connections, but not completely. Right? But essentially what we are saying is that the amount of uncertainty you have in x and y shouldn't really be more than the uncertainty you have in x plus the uncertainty you have in y. All right? Because, okay, where does this additional uncertainty then come from? These are just axioms, mind you. All right? We want a function that satisfies these properties because we feel that it is natural to ask for these properties. All right. And in particular, we want equality to hold if and only if the two are independent of each other. So h of x comma y should be equal to h of x plus h of y if x is independent of y. Right? So in other words, h of p1 q1 up to p1 qn, p2 q1 up to p2 qn, so on PM Q1 up to PM Qn, this should be equal to Hm of P1 up to Pm plus Hn of Q1 up to Qn. This is a requirement that we impose. The last property is that if I make small changes to the PMF, the value of Hm should not change by too much. So it should be a smooth function of P. In fact, it's enough to just have the following. So we have these 6 properties, and we want to know what all functions can satisfy these 6 properties. Okay, and these are natural requirements that we would have in any measure of randomness. It turns out that the entropy is the only function that satisfies these 6 properties.
Sixth property follows for any number of.
It's enough just to do it for 2, and it naturally extends to. So you can show that this coupled with the previous properties implies that h of P1 through Pm is a continuous function of P1 through Pm. We won't prove this particular statement, but this axiomatic approach is one reason why we can interpret the entropy as a measure of randomness, because it is the only function that satisfies these properties. I'm sorry. Again, I don't want to get into it, but basically you start with some of these properties. Particularly, it starts with continuity, and then show that any function that satisfies these should satisfy some properties that summation pi log pi should satisfy, and therefore that's the only function. It's not something that's very easy.
So can you prove this thing? For example, we take the function from f of n, and we take that there are some n power k probabilities.
Okay.
So it will be f of n power k, which is then we group n all some like n probabilities into one single probability. Then it will be f of n power k is f of n plus f of n power k minus.
Okay.
Then it is the property of logarithm.
Yeah, so something similar. Yes, you're right. So, so for example, some property, basically, the property of additivity will kind of force you to will force some kind of properties of logarithms to come in. Using some of these properties, you first show that you can decompose Hm as a sum of functions of Pi, and then use the rest of the properties, normalization, expansibility, and so on, to show that, that's the right choice. All right. Okay. So we've seen discrete entropy. We've seen entropy, mutual information, KL divergence, essentially for discrete distributions. So a natural question is, what can you say about continuous distributions? And there's nothing that stops us from defining these quantities for continuous distributions. So we define the entropy as summation Pi log 1 over Pi. So a natural way of defining an entropy for continuous distributions is integral from minus infinity to plus infinity fx of x. Suppose that x has PDF fx and I can define an entropy in the following manner. This is not called the entropy of the continuous random variable, it's called the differential entropy. All right. No, that's only for discrete entropy. In fact, many things just break down for differential entropy, as we'll just see. So unlike discrete entropy, you can't say that h of x is a measure of randomness in the random variable of the distribution fx. All right. Primarily because even the most basic requirement that we would have, that is non-negativity, does not hold. Okay. In fact, many other things don't hold. So let's just start by calculating the differential entropy for some simple random variables. Let's take the uniform random variable from, say, 0 to alpha. So suppose that x is uniform 0 to alpha. What would be the differential entropy of x? Yeah? Just log alpha. Right, and in principle, alpha can be anything. It can be greater than 0, it can be less than 0. So if I take alpha to be, let's say, half, then h of x is minus 1. If I take alpha to be 1, so uniform distribution from on the interval 0 to 1, the differential entropy is equal to 0. So I can't really say that this measures randomness. Right. And more importantly, even in this particular example, let's say that I have x, which is uniform from 0 to 1, and y is equal to alpha times x. Right? Y, the mapping from x to alpha times x, it's an invertible map. Right? In the case of discrete entropy, we know that any invertible mapping does not change the entropy. It doesn't change the amount of randomness that is present in the system. But in this case, the differential entropy of x is 0, but the differential entropy of y is log alpha. In fact, log of mod alpha, because alpha can potentially be negative. In fact, here's an exercise for you. So for any random variable x continuous and y equal to, say, alpha x plus beta for some real numbers alpha and beta, find the differential entropy of y in terms of the differential entropy of x. This is just an affine map. It's invertible, but you'll see that you can get any value of h of y just by varying alpha and beta. Also, the important thing in this exercise is to see what happens when you shift the distribution and also when you scale the distribution. Each of these changes the differential entropy in a different way. So we'll investigate differential entropy and so on, and what it means maybe in later parts of the course. But for now, I just wanted to introduce this quantity. Even though differential entropy has these kind of weird properties, we can still define the mutual information as the differential entropy of y minus the differential entropy of y given x, the conditional differential entropy of y given x, which is also equal to h of x minus h of x given y, and you can show that this is non-negative. All right, and the reason why this is non-negative is because, once again, the mutual information can be represented as a KL divergence. So the KL divergence for any pair of PDFs can be written as, again, I'm assuming that fx and gx have the same support, so they're non-zero over exactly the same interval, but this can be extended a bit. And which can also be written as expectation with respect to gx of fx of x by gx of x log fx of x by gx of x. And this quantity is always non-negative, but just by Jensen's inequality. Using exactly the same approach as we did for discrete entropy, this KL divergence, discrete KL divergence, this KL divergence for two densities is also non-negative. So the mutual information Ixy is basically just the KL divergence between fxy and the product distribution fx fy. Which is guaranteed to be non-negative. And just as we had in the discrete case, all of the chain rules still continue to hold. So all of the properties that we've seen, all of the, for example, chain rules that we have seen for discrete entropy and discrete mutual information still continue to hold for the differential entropy as well as mutual information for continuous random variables. The only thing that fails is are two things. One is, of course, the interpretation of the differential entropy as a measure of randomness. That's not true. You can't interpret differential entropy as a measure of randomness of the continuous random variable. The second, it's not really a measure of compression, because after all, you can't really do lossless compression for continuous random variables, can you? You can't represent a continuous variable using any finite number of bits. But we'll see where the entropy and mutual information arise for continuous random variables when we talk about lossy compression later on. All right. Any questions? Both of them still okay. Data processing inequality still continues to hold, even if you have x, y, z forming a Markov chain where x, y, z are continuous random variables. You still have I of x, y being greater than or equal to I of x, z. That is still true for continuous random variables. Now, Fano's inequality, you have to keep in mind that you have a random variable x, y, and x hat. And when you say the probability of error is probability that x hat is not equal to x, that makes sense only if x and x hat are discrete random variables. So x and x hat should be discrete random variables, but there's no such requirement on y. Y can be continuous, that's fine. All right. So h of x given y, note that even though y is a continuous random variable, x is a discrete random variable. So if you take the joint distribution of x and y, it's a mixture distribution. It's neither discrete nor continuous. All right, and this is equal to essentially integral minus infinity to plus infinity h of x given y equal to little y times fy dy. This definition makes sense, and once again you have that h of x given y. Fano's inequality says that h of x given y is less than or equal to h of x given x hat, which is upper bounded by the binary entropy of PE plus PE log cardinality of x. This continues to hold. So another consequence of the non-negativity of mutual information is that this still happens. H of x given y is always less than or equal to h of x. So conditioning again cannot increase the differential entropy, just as we had for the discrete case. The only thing here is that h of x can be negative, and if h of x is negative, then h of x given y is going to be potentially more negative. Any questions?
This is H of x in the last line. Is it only when x is discrete and y is continuous?
Yes. Again, because we want h of PE, right? So probability of error makes sense only when x is discrete. If x and x hat are non-trivial joint distributions, continuous distributions, then PE would be equal to 1 with prob. So there would be unequal with probability 1 in general. So it's most useful, and therefore a lot of this just makes sense when x and x hat are discrete.
What is mutual information of x and y?
Mhm.
Represent if x is discrete and y is continuous. How can we write the formula?
If x is discrete and y is continuous, again you have h of x given y, it's h of x minus h of x given y. That still makes sense, right? So let's say that if x is discrete and y continuous, right? For example, let's say that x is Bernoulli half and y is equal to x plus some Gaussian noise. That's a natural way where such a situation can arise. So in this case, the mutual information is h of x minus h of x given y. And this is also equal to the differential entropy of y minus the conditional differential entropy of y given x.
How can we represent it in a form of k level?
Okay. That's a good point. So you have to be a little careful about how you define the KL divergence. Again, in that case, you have sort of a joint distribution, all right? The most, I don't want to get into too much of the technical details, but you can define the KL divergence in far more generality than, for example, when f and g are both densities. All right. So, formally speaking, suppose I have two distributions, px and qx. These are distributions on some common probability space, that is, we have a common omega and f with the property that qx such that px of any event A equal to 0 if qx of that particular event is equal to 0. So there's no event A for which qx of A is equal to 0 and px of A is non-zero. This is a pair of probability distributions on some corresponding to some experiment or some probability space, formally speaking. Okay. In this case, it turns out that you can define something similar to a ratio of two densities. All right. All right. Then so there exists some some function which I'll call dpx by dqx with the property that the expectation with respect to qx of dpx by dqx, this just gives you px. All right. Let me put it another way. Yeah, let's so this quantity is equal to px of a. All right. So this particular notion is called absolute continuity, and this function is what is called the Radon-Nikodym derivative of px with respect to qx. This can be generalized a little bit further. So in principle, when do you say that a particular distribution has a valid density? All right. When does there exist a probability density function for a given probability distribution function? Not all distributions have a density. There are some weird distributions for which densities don't exist. And that happens when there exist distributions for which there are sets for whose measure is equal to 0, that is, whose length in the regular sense is equal to 0, but the corresponding probabilities are non-zero. For example, you take a discrete distribution. Right? A discrete distribution does not have a density because it essentially violates this particular property. If you take any finite set, what is the length of this set? It's 0, right? But on the other hand, what is the probability of that particular set? Something that is non-zero. So for such distributions, a density does not exist. So a density is in some sense a Radon-Nikodym derivative with respect to what they call the Borel measure. Okay. Again, so this basically this kind of quantity makes sense. So you can define the KL divergence between two distributions, two arbitrary distributions, as expectation with respect to the distribution Qx of again, this is not particularly important. It just gets into a lot of technicality more than anything else. For our purposes, we can just go ahead and use one of these definitions for the mutual information. So this kind of formalism allows you to look at mixture distributions and so on. All right. So there's a lot of theory that goes behind it, but that doesn't give you a lot of intuition, so we'll just throw it under the rug. Okay, and whenever we want to talk about mutual informations for mixtures of random variables, say between a continuous random variable and a discrete random variable, we'll typically just use this. All right, but yeah, that's something to just keep in mind. If you just want to know more, you just look up what is a Radon encoding derivative. That's it. Okay. Any other questions? All right. So we'll now sort of switch gears. So far we looked at these information measures and properties of these information measures. But remember, we started out with just trying to understand compression. All right, and we first looked at variable length compression and optimal variable length compression. Now we'll continue along that theme and try to design good compression algorithms, variable length, zero error compression algorithms, and we'll see some of the flaws that are present in the optimal compressor and try to see how to make up for those flaws. Right, again we have this familiar setup. And for now, let's just assume that xn is a memoryless source. So it has independent and identically distributed components, all coming from a known distribution Px. Now for this, what I could do is just design the optimal compression algorithm. So the encoder, since it knows n and Pxn, it should either be given the whole table, the encoding table, or it constructs the encoding table from n and Pxn. And the decoder also has to have this particular information. But now we run into a problem that if n changes, same distribution, same Px, but let's say you go from n to n plus 1, then you would need to reconstruct the entire table, right? Because the order of the sequences is going to completely change. So that becomes a problem, right? Because for every, let's say that I just change the file size, I need to construct a new table again and again and again. That's computationally very intensive, or it requires huge storage space of the table. So what's a more natural approach? A more natural approach is, let's say I encode sequences symbol by symbol. So one way of simplifying or trying to reduce the complexity is to do symbol-wise compression. Where the encoding of x1 through xn is just a concatenation of the encodings of x1, concatenation of encoding of x2, and so on. this is very nice because now the computational complexity is independent of n. I just get a sequence of symbols, I encode them symbol by symbol and done. The decoder, I just start reading from the beginning, I keep decoding symbol by symbol and we are done. Right? So this is computationally very efficient because the complexity doesn't depend on n. I don't need to recompute things depending on what is the value of n. All right. But then we can't really use the optimal compression scheme to do symbol-wise compression. To see why, let's just take a very simple example. Let's say that I have 4 symbols. Say A, B, C, D. With some probabilities. Let's say that probability of A is greater than probability of B, which is greater than probability of C and greater than probability of D. So what would be the code words corresponding to A, B, C, and D in the optimal compressor? Correct. So this would be the empty string, this would be 0, 1, and maybe 0, 0. So this is the encoding. So suppose I want to encode 2 symbols using this particular table. Then what would be the encoding of, say, AD? It would just be 0, 0. Empty string concatenated with 0, 0, which is just 0, 0. What would be the encoding of BB? That's also 0, 0. So now let's say the decoder sees 0, 0. What does it do? Does it output AD or does it output BB? It doesn't know, right? So it's impossible for the decoder to recover either of these 2 symbols. Which means that if you want to do symbol-wise compression, you need to take into account these additional constraints. That concatenation of code words should be such that you can still recover the individual symbols. Okay? Let's just take this example. Did you understand this particular example? Okay. So I started off with a toy example where I have 4 symbols in the alphabet, and I assume that probability of A greater than probability of B greater than probability of C greater than probability of D. All right. So what would be the optimal source code? Optimal source code is you sort the symbols in decreasing order of probability and assign code words of increasing length. So the first symbol would therefore get the empty string as code word. The second symbol would get 0 as the code word. The third would get 1 and the fourth would get 0, 0. Okay. So this is the encoding of per symbol encoding. Now suppose I want to use this to encode a sequence of symbols just by encoding it symbol-wise. So if the source outputs AD, then this would be encoding of A concatenated with encoding of D. Encoding of A is the empty string, encoding of D is 0, 0, therefore I get 0, 0. What about encoding of BB? That would be 0 followed by another 0. So this is what the encoder does. The encoder's job is just straightforward. It just looks at the table and then outputs based on what it sees in that table. But now how should you design the decoder? Because for the decoder it sees 0, it only sees 0, 0. So there is no way the decoder can distinguish between AD and BB. So this is not a zero error scheme. It's not lossless anymore. Yeah.
Lossless doesn't mean that probability of error is exactly 0.
So whenever we say variable length lossless compression, it means that the probability of error should be exactly equal to 0. Again, the terms are a bit misleading. It also varies from reference to reference. So sometimes people say lossless means 0 probability of error, and almost lossless means probability of error that is very, very small, maybe vanishing as n goes to infinity. But in this course, when I say fixed length lossless compression, it means that we allow a probability of 0, but that should be really, really small. But when I say variable length lossless compression, it means that the probability of error is exactly equal to 0. Okay. Any other questions? Okay. So now how do we design such a compression scheme, a symbol-wise compression scheme that is as optimal as possible, that gives you the least expected length? So let's define some quantities, some terms that will be helpful for us. So for us, we've already defined what a compression scheme is. We've seen what an encoder and a decoder is. So we'll say that a compression scheme, is non-singular if the code words for any two distinct symbols are distinct. Okay, this is what it means to be non-singular. And clearly, the optimal compression scheme, this is a non-singular compression scheme. But it's just that when I concatenate code words together, I don't get a non-singular scheme anymore. So we'll define that as well. The extension C star of so I'll refer to compression schemes and codes interchangeably, and whenever I say a code, it is just an encoder and a decoder. So I have a code over some alphabet x. The extension of this is simply obtained by concatenating the code words for the sequence of symbols. Is x star, and the encoding of say x1 through xn is just the concatenation of so this just refers to symbol-wise encoding. So in this case, if we go back to the example of the optimal compressor, the optimal compressor is non-singular, but its extension is not non-singular. Right? Its extension is singular, because even if I look at the length 2 extension, we see that two different pairs of symbols are mapped to the same code word. So if we want to construct a good symbol-wise compression scheme, then what we require is that every extension should be non-singular, or in other words, the extension should be non-singular. So we'll say that a code is uniquely decodable if its extension is non-singular. So you take strings of arbitrary length. So the encoding of any x1 up to xn should not be equal to the encoding of any x1 up to or x1 prime up to xm prime. Even sequences of different lengths should not have the same encoding. So when we are talking about uniquely decodable codes, we don't even assume that the decoder knows the length of the compressed sequence. It just sees this sequence of bits. It knows that where the sequence of the compressed bits begins and where it ends, and just using that, it's supposed to say what was both the length and the sequence, the source sequence itself. Okay, so clearly that optimal code that I gave is not uniquely decodable. Now, along these veins, I'll demand another constraint. I'll say that a code is prefix free if no code word is a prefix of any other code word. Such a code is also called instantaneous. Again, if we go back to this example over here, this is not a prefix-free code, right? Because 0 is a prefix of 0, 0, and phi, the empty string, is a prefix of all other strings. So let's B, C, D. So 0, 1, 0, 1, 1, 0, 1, 1, 1. Is this code prefix free? It is, because you take the code word for any one symbol, it's not the prefix of any other code word. Okay. Is this uniquely decodable? Okay, someone said yes. Why?
Because two distinct code words are encoded differently. Any two distinct code.
How do you guarantee that?
When we read the string from the start, so whenever
Correct.
we enter the
Correct.
in the table, and then we separate that out and start fresh.
Correct. So basically, one way of showing that something is uniquely decodable is to concretely come up with a decoder. If you can come up with a decoder that is guaranteed to output the correct sequence of source symbols, and without any ambiguity, right? If there is absolutely no ambiguity in the decoder, then it means that it is uniquely decodable. All right. Again, it's not completely formalized yet, but hopefully you get the point. So in this case, what you can do is I come up with the following decoder. I start reading the code word symbols from the left, one at a time. If the first bit is a 0, then I know that the symbol is A. Right? For sure, it has to be A. It can't be anything else. I read the next bit. Then the next bit starts, again I start afresh. If the first bit I read was a 1, then I know that I don't have enough information to say which symbol it is. If the next symbol I read is a 0, then I know that it's equal to B and it can't be anything else. If it is a 1, then it can either be C or D, in which case I read the next symbol. And the third symbol is enough to tell me whether it is C or D. There's no ambiguity left anymore. Another way of representing this is in the form of a tree. You have a decision tree which looks something like this. So this is what I call a code tree. So I start from the root. I read the first symbol. If it is a 0, then I go to the left. If it's a 1, I go to the right. So if the first bit I read was the decoder, if the first bit I read, the decoder read was a 0, then you know that the symbol is A, and then you again go back to the root and proceed. If the first symbol was a 1, then you go to the next node. I don't know what to decode now. So now I read the next bit. It can either be 0 or 1. If the next bit is a 0, then I know that the symbol must be B, and then I again go back to the root and continue. If the next bit was a 1, then I don't have enough information to make a decision. So I read the next bit, which is if it is either 0 or 1, and after that point I know how to make a decision, and then again I go back to the root. All right. So for example, let's just take some sequence, say A, B, B, C, D, A. What is the encoding? Zero, 1 0, 1 0, 1 1 0, 1 1 1 0. Right? Okay. So now you use the tree to decode. I read the first bit. The first bit is a 0, so I go to the left branch of the tree. I know that I immediately know that this should be equal to A. And now I immediately go back to the root. Right? I go back to the root. Next, I read the next bit. The next bit happens to be a 1. I read the next bit that happens to be a 0. So I know that the next symbol is a B. Right? So this is B. I again go back to the root. So at this point I have decoded till here. I read the next bit, which is a 1, and the next bit, which is a 0. So I know that the next symbol must also be equal to B. So I've decoded up to this point, and I know that this is B, B. And I go back to the root. I read the next bit, which is 1, then 1 and 0. So the next it should be C. And again go back to the root. then I have 1, 1, and 1, which is D, and I again go back to the root, I get a 0. At that point I stop, because I have no more compressed bits to read. So I have B, B, C, D, A. So one way of thinking about all of these, unique decodability, prefix-free, non-singularity, and so on, is using code trees, because it gives a very nice visual representation of the encoding and the decoding. So this is for one symbol, right? The encoding and decoding of one symbol can be performed using this particular code tree. In fact, any code, whether it's prefix-free or non-singular or uniquely decodable, can be represented in the form of a tree, right? Because it's just a binary sequence, right? So if I have, let's take maybe 3 different codes. The first, C, D, the optimal code. The second is B, C, D, maybe something like this, which is 0, 0, 1, 1, 0. The third zero, 1, 0, 1, 1, 0, 1, 1, 1. Right, I have these 3 codes. Let's try to represent each of these using a binary tree, in terms of a binary tree. So first, let me draw a binary tree of depth. Okay. So in this case, 0, 1, 0, 0. So the root corresponds to symbol A. This node corresponds to symbol B. This node corresponds to symbol D, and this node corresponds to symbol C. Note that this is part of a complete binary tree of depth equal to the maximum code word length. Let me also do this for the next example. So 0 corresponds to 2 symbols, A as well as B. 1 corresponds to symbol C, and 1, 0 corresponds to symbol D. The first example was something that was non-singular, but not uniquely decodable. So what is, if I just draw the code tree, then how would you characterize non-singular codes?
Completely filled.
Not necessarily, right? In this case, it's not completely filled, right? Because, for instance, these.
The correct one is actually completely.
Which one? What do you mean correct one?
The
Not exactly. So I'm just labeling the nodes with source symbols, right? So what is the definition? Yeah? Well, that's okay, right? Here is an example of a non-singular code. This is non-singular and it's prefix free, and all of them are the leaves. Something much simpler. Nothing sophisticated, something very, very simple.
No two
Yeah.
symbols are same.
Exactly. No two symbols get mapped to the same node in the code tree. That's it. That's all that non-singularity is saying. No two symbols have the same code word, which means that no two symbols are mapped to the same node. Right? So this is non-singular. It is singular if there are two symbols which get mapped to the same node. Do you all agree? Similarly, what about prefix free? What can you say?
What symbol should occur on?
That's just non-singular, right?
Non-singular is
No two symbols get mapped to the same node. That's non-singular.
whatever it is.
So prefix free is one where no code word is a prefix of any other code word. So in terms of the tree, what can you say?
If you look at a symbol where it occurs,
Ah.
then in its successor list it should not appear.
Correct. So another way of saying that in graph theoretic terminology is no symbol is a child of any other symbol, or no symbol is a descendant, to be more precise, no symbol is a descendant of any other symbol. In this case, let's say in the first case, D was a descendant of B and A, C was a descendant of A, and so on. In the second example, D is a descendant of C, and A and B are descendants of each other. Right? So a code is prefix free. I'm sorry. Is non-singular if symbols are mapped to the same node and C is prefix free if is a descendant or ancestor of any other symbol.
This condition would automatically make it stop at the ancestor node, right?
I'm sorry?
This condition would
In which case?
So if I have A and say that node in the last place, then I cannot make the other decision. Or B, so I can't have any descendant. That's what it says.
Correct.
That by default makes it a like end of.
Correct. This in some sense is the end of the tree. Correct. I've just drawn, that's why I've drawn the rest in yellow. But in principle, the code tree is only what is drawn in blue. The code tree is actually just the part drawn in blue, but you can view this as a subtree of the complete binary tree up to depth Lmax, where Lmax is the length of the longest code word. The reason why I'm doing this is because I'll use that in sort of the next steps. All right, but the code tree is essentially all that I have drawn in blue. That's the code tree. All right. Okay, let's stop here. We'll continue in the next class.